In this video, we're going to show how to program Cramer's rule into Sage. So let's begin by recalling Cramer's rule. That it gives a way to solve a system of linear equations of the form ax equals b for a given n by n matrix A and an n by 1 column vector b. And the solution, we're trying to solve for x, and so x is going to be a n by 1 column vector. Here I've used indexing starting at 0 instead of 1, which is what we normally do in math, but in computer science and in Python and Sage, indexing starts at 0, so I've stuck with that. It doesn't, again, matter too much as long as you're consistent. Okay, so Cramer's rule says that x sub j is given by the ratio of these two determinants, the determinant of a sub j, a matrix which I'll tell you about in a second, and then the determinant of our matrix A is what we have to divide by. So first of all, we have to check that determinant of A is non-zero. Then there will be a unique solution. If the determinant of A is 0, well, Cramer's rule doesn't apply. In that case, in the case where determinant of A is equal to 0, there could be no solution. There could be infinitely many solutions. So, but Cramer's rule does not apply. Okay, now what is this matrix A sub j? Well, it's quite simple. You start with A and just replace column j with the column vector b. Okay, so yeah, so let's go to the programming part. So I'm going to call my program or function mySolve, and it accepts A and B. These are the matrices, and we have to solve for x. It's going to return x. And again, the notation for writing a function in Sage is, def, then the name of your function, and then followed by the variables it takes as input, and then followed by a colon. Now, the first few lines are doing some just error checking, if you will. So first, I'm checking that A is a square matrix. Cramer's rule only applies to those situations. So I check that the number of rows of A is not equal to the number of rows of number of columns of A. And if they're not equal, then it's not a square matrix, so I return this error message that the first matrix is not a square. Okay, so then if it is a square matrix, we can compute its determinant, and we have to check that the determinant is non-zero in order to apply Cramer's rule, because again, Cramer's rule has determinant of A in the denominator. All right, so then here's a line where we check that the determinant of A, well, we're checking, is it equal to 0? And so what's important to use is the double equal sign. That's the comparison operator. If I'd use a single equal sign, that's the assignment operator, and that would give problems. So you definitely want to use the double equal sign, don't forget the colon. And so this is saying that if the determinant is equal to 0, then return another error message that the first matrix has determinant 0, so Cramer's rule doesn't apply. Okay, then if we've passed these two error possibilities, then there's maybe a third error possibility here in this line, and it says I want to check that B has the right size. In other words, the number of rows of B, I want it to equal the number of columns. And if it's not equal, so here's the notation for not equal, the exclamation mark equals, then return an error message, and then or also return an error message if the number of columns of B is not equal to 1. I want B to just be a column vector. Okay, so then now we'll get on to the important part of the main part of the program. So let n be the number of columns of A. Let x be a n by 1 matrix that's going to contain our answer eventually. And yeah, I chose entries in the rational numbers. Okay, so then the main loop is that for j in range n. So remember, range n is the integers from 0, starting at 0 and ending at n minus 1. And that's how the columns of this matrix A are indexed in Sage. Starting at 0 is the first column, and because it's an n by n matrix, the last column is labeled n minus 1, or numbered n minus 1. Okay, so then I'm going to create this matrix A sub j. So remember, A sub j in Cramer's rule is you start with the matrix A and replace column J with B. So that's what's happening here. A sub j, I start with A. Now, I discovered while making this tutorial, I have to use this word copy A. And that's because if we don't use copy, then when we change A sub j by replacing a particular column, we're also going to change A. It's just a funny quirk of how Python works, and involves, references and pointers and things in memory. But okay. Anyway, so A sub j is a copy of A. So basically it's the same as A, but a different spot in memory. Okay, and then this is the line that replaces column J with B, the vector B, or the column B, column vector B. So this AJ brackets colon J refers to the column J, and the equal sign is saying assign that column J to be this column vector B. So again, this is the line that changes that column to B. Okay, and then once we have this matrix AJ, then we just apply this cramers rule, compute the determinants. Sage has the built-in determinant function, and AJ.determinant divide by the determinant of A, and then so that is underneath this for loop. And then again, indentation is important. Now I put outside of this for loop, so not indented, I put return x. Okay, and right, let's check it out. So I compute a random matrix, a 3x3 random matrix. I allowed the coefficients to be in Z. I could have also put Q. And when I ran it, this is what the matrix it came up with. Sometimes it gives a matrix of determinant 0, but this time it gave a matrix of non-zero determinant. Then I cooked up a column vector B, a specific one, but I could have chosen to choose a random matrix. Okay, and then I apply my mySol function that I just wrote, and it gives some answer. And then I compare my answer, I guess, to the one that the built-in solver that SageMath has. The notation or the syntax for using that is A solve right B, and that gives indeed the same answer. And then as a third or second check, I guess, you can do A times the answer that mySolve gave back, and that does indeed give back B, because remember, A times X should equal B, and that's indeed the case here.